Hi, this is Dr. John Bergduff. We want to move towards the formal definition of dividing fractions and the process that we want students to learn for dividing fractions. But we want to find some ways to motivate those rules so they're not just something you memorize for no particular reason. Illustrating division of fractions can be a little tricky. I'm going to show you a couple things. One is a pretty good model for some very simple examples. The other will help with a little bit more difficult ones. Now I'm going to start by asking a question that seems totally irrelevant to the idea of dividing fractions, but it's going to help us get somewhere. Suppose you're looking at the simple division of whole numbers 6 divided by 3, and we all know that that's a 2. One way to look at that is in thinking about how you might model just a simple division like that is by asking how many 3's are in 6. If you had, for example, 6 small circles and you were asking yourself, well, how many 3's are there? Well, there's 3 circles, there's another 3 circles, 2 groups of 3. 6 divided by 3 is equal to 2. How many 3's are in 6? And that might be something you might explore in a very early grade, just to get the general idea of division. Let's take that a step farther and think about whether that can be sort of translated into a division by fractions. Suppose we're looking at 4 excuse me for a second here. Oh, I see what's wrong. 4 divided by a third, and ask it the same way. How many 1/3 are in 4? So asking that in a similar way. Like we drew 6 little circles to represent 6, let's do the same thing with 4. I'm going to make them a little bigger. How many 1/3 are in there? Well, each one of those fractions could be divided up into thirds. And then if I were to count how many 1/3 I see in those 4's, I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many 1/3 are in 4? There's 12 of them. Now, let's look at that a little bit more carefully. So what does that mean? 4 divided by 1/3 is 12. Well, that certainly looks like the same thing you would get if you multiplied 4 times 3. That would also give you 12. It looks like what we do is we take the second fraction, and we flip it over, make it from 1/3 to 3/1, and that gives me the result. Hang on to that idea. That does look very much like the idea of division. Multiply the first by the reciprocal of the second. Now, this model gets a little bit more difficult when you have 2 fractions, not whole numbers. Suppose you have 7/8 divided by 3/5. How many 3/5 are in 7/8? That gets really hard to visualize. So I'm going to approach this with a different model. Again, when you're exploring division for the first time, you might explore division, let's go back to 6 divided by 3, using what's called a missing factor approach. What is 6 divided by 3? Suppose you don't know what that is, and you say, well, I'm just going to put a box here. I don't know what that means. This is equivalent to saying 6 is equal to 3 times what? What would I have to multiply by the second number, the divisor, using formal terminology? What would I have to multiply by the second number to get the first number? Well, it's then a matter of filling in the box. 6 equals 3 times 2. 2 is what you have to multiply by 3 to get 6, so 6 divided by 3 is 2. Maybe that approach could help us here. Let me start with a clean slide. The question was 7/8 divided by 3/5 equals what? We don't know. But what it is whatever you would have to multiply by 3/5 to get 7/8. What goes in this box here? Well, I'm going to kind of cheat a little bit. If I were to put in this box 7/8 times 5/3, that would actually get me a true statement, because in looking at the multiplication, I see a 3 in a numerator that would divide a 3 in a denominator, and a 5 in the denominator that would divide a 5 in the numerator. So basically, by putting the 7/8 times this fraction flipped over, that is what would go in the box to make this true. So 7/8 divided by 3/5 actually turns out to be 7/8 times 5/3. Then I can use the rules I already know about multiplication that say that to multiply two fractions, I multiply the numerator by the numerator and the denominator by the denominator, and that's what I get. That may have been a little fast. Let me do another one so that we can illustrate this again. What if we had 3/4 divided by 9/10, let's say? What I need to say is, what would I multiply by 9/10 to get 3/4? And the simple trick is, if I put the 3/4 and I take the 9/10 and invert the numerator and denominator, flip it over, that will work, because this 9 divides that 9, this 10 divides this 10, the result would be 3/4. So 3/4 divided by 9/10 has to be the same as 3/4 times 10/9. That's right at the definition of division, right there, using this missing factor approach. Now I could go ahead and say 3 times 10 is 30 and 9 times 4 is 36, but the more efficient thing to do before I do that multiplication is look to see if there's anything that might divide out. I notice that the 4 is 2 times 2, 10 is 2 times 5, 9 is 3 times 3, factoring everything into prime factors, and then I see a number of factors that will divide. The 3 in the numerator divided by the 3 in the denominator is 1. This 2 in the numerator divides one of the 2's in the denominator, just pick one. And looking at what's left, in the numerator there's nothing left but a 5. And in the denominator, 2 times 3 is 6. The answer is 5/6. So that leads to the formal definition of division. Let A, B, C, and D be integers. And let's say that the B can't be 0 and the C can't be 0 for reasons you're about to see. And actually the d can't be 0 either. A over b divided by c over d, so you can see why b and d cannot be 0 here, is equal to a over b times d over c. Take the second fraction and flip it over. The fancy word there is the reciprocal, and then that becomes a times d over b times c. And you can see why c can't be 0 either. The way that is usually stated in words that makes it easier to follow is to say that to divide two fractions, we multiply the first by the reciprocal of the second. But hopefully these two models, the area model for simple fractions and the missing factor model for more complicated fractions, gives a reason to motivate why division is done the way it does, and hopefully that will help your students feel more comfortable. Thank you very much.